Okay, so now we'll try to tackle a significantly more difficult question than its neighbors on this channel, and that is, what's the point of quantum mechanics? And let's try to see if we can start with a good rule of thumb in attempting to answer this question. And for ourselves, we'll take the rule of thumb that the most interesting ways in which quantum mechanics has proven to be paradigm shifting, or things to that effect, has been areas in which it has managed to dispose of convention in mathematics and basic scientific methodology. And we might take two very enlightening illustrations of this fact. The first has to do with the mathematics of quantum mechanics. All right. So you probably know by now, if you've interested yourself, occupied yourself with quantum mechanics to any significant degree, and with the right sources, that the mathematics of quantum mechanics is all about probability. And probability is one of the most heavily studied segments of mathematics throughout its history. The French mathematician Laplace even wrote a giant treatise on probability in which he purported to explain everything. He suggested that he has managed to come up with the ultimate program to model everything in the universe, which is what we today call the ideas of probability. Now, quantum mechanics, strangely, despite the massive body of work in mathematics on probability, was forced to invent a few new ideas in probability in order to account for various experiments. And this was why it was troubling and difficult for scientists of the time and of the present to absorb or accept instantly without any noise. So the idea that quantum mechanics pioneered was that in various physical situations, we must replace the probability, which is a number that the situation will occur, with an arrow pointing in some direction in 2 dimensions. Little strange, right? But that was it. That's the entire point. The proposal by the people who had to tackle the mathematics of quantum mechanics was we can use all the basic ideas and the basic logic and the reasoning that we've learned in probability theory, only every now and then we have to replace the number probability with an arrow in 2-dimensional space. That's it. It's as simple as that and as weird as that. To this date, no one has been able to explain why exactly we need to replace the numbers by arrows and what the significance of these arrows are. Most scientists have, as they say, given up and said that there is no significance to the replacement of numbers by arrows. But there you have it. There are still some scientists who spend a lot of time and energy on trying to seek out an answer to this very fundamental question. This is really the first of the two main origins of the strangeness in quantum mechanics. The other has to do with scientific methodology. And this has to do with something that happened quite a few years after the basic principles of quantum mechanics had been laid out, that is, the mathematical principles. Towards the end of the 1920s, a young German student named Heisenberg said that he had finally discovered the rational significance of all the weird mathematics that quantum mechanics was using, replacing probability by arrows and all of that. He said, let's not get carried away with the fact that we're replacing probabilities with arrows and all of that, and instead take a look at some of the consequences of this mathematics. One of the main consequences is that in any given physical situation, let's say a small atom near a magnet, of the basic set of parameters that we learned to use in high school mathematics to calculate or determine the behavior of this atom near the magnet, we can determine only one or the other with perfect accuracy at any given moment. Now, this is not exactly what Heisenberg said. he said that there is a trade-off in the accuracy in measuring these two parameters, what we call the position and the momentum of any object. And these two parameters are the basic ingredients to most problem solving in physics, are really the solving of the fundamental problem in physics, determining the motion or the behavior of an object upon which a certain force is being exerted. Heisenberg comes along and says that it is in the nature of measurement that we cannot measure these two basic parameters with perfect accuracy at any given moment. Now, note that I am using the word accuracy in contrast to precision. Some popular science books might use these interchangeably, but it's really very significant, the difference, because you can, even in Heisenberg's scheme, measure both of these parameters with any precision that you'd like. The point is that when you measure them again, one of them will be vastly different from the other. When you measure them again, the value of either of them might have changed drastically. And the trade-off is between the extent to which the values change. This is a bit of a headache, I can see, but Heisenberg proposed that this was actually a rationalization for the use of these strange mathematical ideas in quantum mechanics. And the other pioneer of quantum mechanics, Niels Bohr, took this a step further. He said we have to replace all scientific methodology, all conventional scientific methodology, with a new one that starts to understand the problems inherent in the process of measurement, the process in which a measuring apparatus has to interact with the parameters being measured and how they affect one another. And this was a really, really painful blow to scientists, because in the first place, they already had to deal with this very strange mathematics that did not exist before. Physicists sometimes take it for granted that they do not have to invent any new mathematics. You only have rare cases like Sir Isaac Newton, who had to invent calculus in order to solve all the problems in physics he was concerned with, which was basically almost all the problems in physics. But more often than not, physicists take it for granted that they do not have to invent any new mathematics. Well, finally, a scientist like Heisenberg comes along and says, all right, let's not break our heads over this new mathematics. See, I found an explanation for why we had to adopt a new mathematics. We have forgotten that measurement is a very complicated thing. And this, far from being reassuring to physicists, actually created greater frustration, because in the first place, they could not rely on their old instincts of referring to all well-established mathematics. And in the second place, even the basic tenets of scientific methodology were being threatened by these new ideas. And that really is the source of all the strangeness, very legitimate strangeness associated with quantum mechanics, as well as the hype. This cannot possibly suffice as a good answer to the question, what's the point of quantum mechanics? But the question in itself is far too great to handle in a short period of time, as we have endeavored to. So if you want to know about the subtleties behind the question and a little more about quantum mechanics itself, head on down to the Centaur Courses and we'll chat. Okay, thank you for listening.